Thank you for giving us the opportunity to present our recent work, providing application access to voice streams, enhancing push-to-talk services for emergency response. I'm K.K. Ramakrishnan from the University of California, Riverside. This is work done in collaboration with Jiachen Chen from WinLab, Rutgers University. Mission-critical push-to-talk, MCPTT for short, have been a key communication tool in emergency response as it provides the ability to have interactive communication with other team members for reacting to urgent needs, coordination, and better overall situational understanding. Existing systems and research has focused on the mouth-to-ear latency of systems to deliver voice streams. For this, it becomes natural to deal with the voice in the operating system and leave the application only the control of calls and the floor, since it can be more efficient and thus reduce the latency by not going through the application for audio recording and playback. But it is important to provide applications the capability to manipulate the voice stream to provide features that are critical for first responders. Our conversations with first responders indicated that the time wasted on the MCPTT communication is caused both by inconvenient functionality available for users, the interfaces, and the protocol level interactions, for example, allowing concurrent flows and the ability to have D2D communication. In this work, we propose next-gen MCPTT, a system that aims to improve the efficiency of delivering mission-critical communications. We built our implementation starting from the base of a mission-critical open platform, MCOP SDK. We made modifications to the lower-level components of MCOP so that the service layer not only packetizes the voice streams, but also gives applications full control of the voice data. With this capability, we allow applications to serialize the conversation on the receiver end instead of asking the speakers to serialize their speaking by waiting to acquire the floor. The voice can be played on demand or even replayed as needed in order to save time of first responders. At the same time, the devices can store and forward messages among themselves to provide device-to-device communication in infrastructure-less environments. We also take advantage of speech-to-text and text-to-speech capabilities to make it more convenient, potentially accelerating communication among first responders through asynchronous communication in difficult emergency situations. In this presentation, we will discuss several features enabled by our new design. A simple and obvious case with traditional MCPTT systems is the difficulty in users having to serialize speech. This can be especially disruptive and inefficient on a connection with long delays, for example, a satellite link. First responders end up wasting a lot of time waiting for the floor or just talking over each other. We consider a scenario as shown in the figure below. User 1 is sending a long report from T1 to T4. At T2, user 2 wants to interrupt and speak. In traditional MCPTT, since the floor is occupied by user 1, user 2 has to wait till user 1 releases the floor at T4. Any other listeners on the channel, like user 3, can only hear user 2's voice after user 1 finishes. In an extreme case, if user 1 does not release the push-to-talk button on time by accident, the whole channel is blocked and therefore no one can send anything, nor can anyone notify user 1 to release the token. This could result in important messages being delayed. At the same time, frequently waiting for the floor also wastes a lot of precious time of the first responder, which can be used instead to save lives. In our solution, since the application gets the access to both the incoming and outgoing voice streams. It can allow the first responders to speak whenever they want to. We call the new communication scheme push and talk. As shown in the figure, user 2 can just press the button to speak at T2 without the need to wait till T4. The application holds the outgoing messages and delivers them whenever the channel becomes available. This saves the time of user 2 since he or she does not have to wait for the floor to speak. This also applies to the scenarios where user 2 is offline or has intermittent connectivity, for example, with satellite links. The application can store the outgoing voice and the user does not have to worry about the channel availability. We notice that in these scenarios, the messages could be delayed to provide first responders better context awareness. The application carries the send time of the messages, showing them on the user interface. We'll talk about the user interface a bit later. In channels with higher bandwidth, allowing multiple voice streams to be delivered concurrently, the application can even deliver user 2's voice immediately starting from T2. The application on the receiver end can then serialize the speech depending on the user requirement. For example, for user 1, the voice will be played after he or she finishes the speech. User 3 can even switch between user 2 and user 1 speech as desired between T2 and T5, allowing urgent messages to be heard earlier. In next-gen MCPTT, the application has full access to all the incoming messages and can control when each one should be played. It can present the user a conversational view to provide first responders a view of the interactions within a context. The user can select a group or a private conversation to focus on, and the application only shows and plays the messages within that conversation. On receiving messages from other conversations, the application stores the messages without playing them. Instead, it shows a marker on the top left to indicate the number of messages pending with a short notification sound. Thus, the user does not get distracted by messages that are not urgent. The user can go back to those conversations after the current work is finished and re-listen to the missed messages. While the conversational view helps a user to focus on a context at a time, we do realize the need to prioritize some emergency messages. For example, a commander ordering everyone in the team to retreat from a dangerous situation. Since the application has full control of the video chunks, it is easy to allow emergency messages to override session boundaries to be played immediately, sometimes even preempt an ongoing message. The application can also allow the user to prioritize some conversations or senders, for example, messages from an incident commander, as needed. First responders often have to work in areas with limited or intermittent connectivity, or even without communication infrastructure support. For example, in urban search and rescue activity in the aftermath of an earthquake. In these cases, D2D communications, for example, Bluetooth or Wi-Fi Direct, can be used to satisfy the need for communication among first responders. While many existing DTN solutions support a store and play mechanism to deliver messages under such conditions, they lack a smooth transition between the connected and infrastructure-less environments. Their solution lacks real-time interactive communication even when the devices are connected to the internet. In next generation MCPTT, since the applications have access to the audio chunks received, they can also use it for data forwarding between devices to either extend the coverage range of infrastructure communication service, similar to call forwarding, carry the messages and deliver them to the users in the field, similar to DTN, or even provide local MCPTT delivery in infrastructure-less environments via D2D communication. We start from a server-based solution for normal communication, which provides efficient real-time message delivery. When users have intermittent connections, we pre-build a store and forward mechanism, and therefore, whenever a connection is available, complete messages can be delivered. To allow for range extension with D2D communications, we provide a forwarding mode where one user can forward messages on behalf of another. We allow multi-hop forwarding, forming a tree rooted at the server. When the forwarder cannot connect, the server at the root can also serve as a temporary server to enable communication among users within the shelter. In our system, we allow a device to forward messages for multiple users, but only connect to one upstream device or server. Therefore, users will eventually form a tree rooted at the server. This structure has proved to be efficient, especially when communications have to go through the server compared to a mesh network where routing could be difficult. Since our application has full access to the voice streams, they take advantage of the speech-to-text service to translate every received message to text. This can help first responders in noisy places where they cannot hear the message clearly, or in places where they cannot play the audio. This can also help first responders who might receive a large number of messages so that they can glance through the text and play only the messages whose transcriptions are confusing. We also incorporate text-to-speech capability. First responders can type a message in text, the application would generate a synthesized voice and send the voice to the group. This would be helpful in an environment where the first responders are not able to speak. For instance, when it is noisy. SMS is also natively supported as a variant and can be combined with voice synthesis. It allows first responders to be eyes-free even when they receive text messages. In addition, this SMS could save bandwidth in the common channel to or from the server, since text messages are much smaller compared to the synthesized voice. Our application can use cloud-based text-to-speech or speech-to-text services whenever the devices are connected to the internet. To help first responders without internet connectivity, we can also deploy services on a machine directly in the field. There are a number of scenarios we haven't covered here in this presentation due to the limited time. For example, multitasking and map integration. Please look at our paper for more details on those aspects. As a quick conclusion, in this paper, we presented next-gen MCPTT, a novel system that improves mission-critical push-to-talk services by enabling features like push and talk, providing a conversational view, multitasking, device-to-device communication, text-to-speech and speech-to-text support, and map functionality that are all very well suited for first responders to use during emergency management. The fundamental changes we made was to not only packetize voice clips, but also give applications full control of the voice streams. Thus, applications can easily manipulate the voice stream in the way they want and present the messages to first responders appropriately. We demonstrated our application and had several first responders try our application out in their training exercises at Disaster City at Texas A&M University. Their feedback was that the new features saved them a lot of effort in communicating and helped them focus on their work during the exercise. Our future work includes: 1. We plan to integrate our application into ATAC, the Android Team Awareness Kit, so that more first responders can take advantage of the application in their real work. And 2, we plan to explore other wireless technologies like LoRa to provide better D2D coverage in infrastructure-less environments. Finally, we also need to quantify the increase in the mouth-to-ear latency because of our design. We foresee that more applications can take advantage of the exposed audio data and provide even better service to first responders. Thank you very much. Please visit our website and feel free to contact us if you have any questions.